please mute yourselves as much as you are willing and or able to do so. And with that, I would like to introduce our featured speaker for the evening, which is Michael Lucas. He will be talking about TLS Mastery. And in case you haven't actually picked up the book yet, there is a very beautiful book that you can pick up along about TLS Mastery. This one happens to be the hardcover version, and it comes both in BSD and Linux variants as well. He's also the author of several other very important books, such as SSH Mastery, Networking for Systems Administrators, and the Networknomicon, which is your go-to resource for how to become completely and utterly mad in using SNMP. And also the seminal work, Ed Mastery, the only editor that you will ever need. And in case you weren't fully aware of the absolute brilliance of Michael Lucas, he also has the book Only Footnotes, which does what it says on the tin and gives you only the footnotes, which are the most important parts of the book. So anywho, I'd like to introduce Michael Lucas. You are muted, unfortunately.
I don't think I can possibly live up to that introduction, but I do thank you. Hello, folks. My name is Michael Lucas, and I am trying to share my screen. Here it is. Share my screen. And can you see that?
We can.
Okay. Now, the last time I was here, I gave my talk on SNMP, not realizing that I had become disconnected immediately after the title slide. So I've taken a couple steps to prevent that. And one of them is apparently my nice desktop with 3 monitors blows up on Jitsi and disconnects randomly. So this is a special version of this presentation made without any of the notes that I would normally be reading on a second screen. And I'm going to be checking now and then to see if anybody can hear me, and if you are still connected. So, I have been using Unix since sometime around 1987. If I had known how important it was going to be, I would have taken note of the date. And that picture is me with 1 copy of every book that I have written or appear in. I need a new hobby. So, what's in this talk? We're going to talk briefly about what TLS is, what certificates are, how certificates can be revoked and invalidated, how TLS negotiation works, certificate signing requests and ACME, some of the edges of TLS that you may not be aware of, and then some on being your own CA. And we only have about an hour. I know Mug lets me ramble on a little longer, but I would like us all to be able to get offline without too much waiting around. So I'm going to mostly focus on web servers. This talk is based on Openssl 1.1.1 or LibreSSL. And the platforms I used for reference were CentOS, Debian, FreeBSD, and OpenBSD. Are you still there?
Yes, we are still here.
Yeah.
Okay.
Yeah.
When you ask that, it takes all of us a few seconds to find the unmute button.
I'll tell you what, Craig, I'm at every couple slides, make a noise. I'm hereby delegating Craig because I'm not giving this talk a second time like I did with SNMP.
Right.
Boop.
So, what is transport layer security not? There's a whole bunch of things that it doesn't do. It doesn't add security. It doesn't block intruders. It doesn't keep your credit card secret. It doesn't stop password theft. It does none of these things.
Okay, wait. Does this work on the transport layer of the 7 layers ISO OSI?
Yes. Yes, it does. Well, what it does do is it encrypts traffic between the client and the server. It can also identify the server or the client or both. That's it, nothing more. I will often hear someone say that they're using TLS so their web store is secure. And no, it's not. TLS protects one tiny piece. But if your software for your shopping cart is crap, TLS will do nothing to protect it. So, TLS was created in 1994. Netscape, the folks who wrote the original Netscape web browser, wanted e-commerce to be a thing. They needed a protective layer. They developed Secure Socket Layer 1 in-house and sent it out into the world. Any cryptographic protocol designed in-house is doomed to fail. So they very quickly rushed SSL3 out, and then, SSL2, and then rushed SSL3 out. SSL3 managed to last a couple years until they released TLS version 1. TLS is SSL. The name was changed entirely for political reasons. There's a whole bunch of sordid detail in the IETF mailing lists. And TLS has been incremented for a while until in 2018, TLS 1.3 came out. More than one cryptographer has told me that TLS 1.3 is the first version with a solid cryptographic design. It took 10 years to develop. It was solidly pounded on. Hopefully, TLS 1.3 will be around for a good long time. Okay, how many of you folks remember John Postel? If we were online, if we were in Meet Space, I would ask you to raise your hand, but we're not, so don't bother unmuting. I'll just assume everyone remembers. Postel was such a primordial engineer of the internet that he had the original listing of IP address assignments in a paper notebook that he kept in his desk. If you needed IP addresses, you emailed him. He looked at the notebook, he wrote down the next block and sent it back to you. And he proposed this principle of be conservative in what you do, be liberal in what you accept from others in internet protocols. And we apply this throughout the internet today. If you have a modern web client, chances are it speaks old versions of HTTP. Maybe it doesn't support the blink tag anymore, but you can get something out of these really old servers. Database engines can probably still speak older versions of the protocol. Same with SMTP. Excuse me. I can still telnet to port 25 on a mail server. And so long as I don't use the actual hello command, I can send mail by hand. Even DNS still mostly works. With TLS, Mr. Postel's rule has some very bad effects. There's something called a downgrade attack that allows man-in-the-middle attacks. Suppose I can get between you and Amazon, and I can convince Mr. Bezos to speak to your client using SSL version 3. I can decrypt everything that happens between you. I can interject my own traffic. I can execute a very nice man-in-the-middle by persuading this connection to drop down to a faulty encryption technology. And this downgrade attack applies to all sorts of encryption, not just TLS. You need to configure your servers and your clients to reject weak encryption methods. I'm sorry, Mr. Postel, we still love you, but this is the exception that proves your rule. So, all versions of TLS except 1.2 and 1.3 are known to be bad. If you're still supporting even TLS 1.1, you are threatening your customer data, your business, and everyone's privacy. Turn that crap off. In early 2021, the US NSA strongly discouraged many TLS 1.2 configurations. We cannot yet disable TLS 1.2 on general websites. There is no government standard compliant TLS 1.3 browser. But the NSA has this distressing tendency to predict cryptographic attacks. So when they say don't use certain configurations, listen to them. You can find that pretty easily with a Google search on NSA and TLS 1.2. So let's talk about encryption for a moment. Encryption is an incredibly specialized skill with many pieces. There are very few sysadmins who really understand cryptography. If you are not doing the math, if you are not working with the actual algorithms and your calculator and figuring out how all of this stuff really works, you're not really qualified to have an opinion on how strong algorithms are. The responsible thing for us to do is to trust the cryptographers. And yet sysadmins have this distressing habit of having opinions because they've heard something and it sounded right. For encryption, the best practice is to follow what Openssl calls the high cipher list. This is the stuff that is known to work. And it updates for you whenever you update your Openssl. A couple other things you should know about encryption is you have a private key for every certificate, for every application that uses encryption. Protect that private key at all cost. And for certificates in particular, revoke your certificate anytime you have any doubts, and we'll get into all of this. Now, are you still there?
Boop.
Boop, thank you. The big problem of any cryptographic framework is who to trust. This is the big screaming problem of cryptography. And there are two general competing models. One of them is the web of trust that's used by OpenPGP and friends. Many of you have probably used PGP. You have attended or heard about a key signing party and signed one another's OpenPGP keys. And basically, the web of trust says, you know, I trust Craig, who trusts Gib, so I will trust Gib. And that's great, except it requires transitive trust, and it requires educated users. If I trust Craig, it's because I believe that Craig has educated himself on what trust means, and that I believe he's following standards that are sufficiently high for me. Your average user who is buying shoes on a website is not that. That's why we have the other model called certificate authorities, where this highfalutin organization takes on the job of auditing people's identities and digitally signing certificates. Each of these certificate authorities has one or more trust anchors. Basically, they have a certificate. They look at your certificate and say, and they check your driver's license and say, yes, Craig Maloney is who he claims he is, will sign his certificate and send it back. Client software collects a bunch of these certificate authority certificates in a bundle called a trust bundle, trust anchors, ultimately trusted certificates, or root certificates. There are 6 major trust bundles: Microsoft, Apple, Google, Mozilla, Adobe, and Oracle. Openssl most often ships with the Mozilla bundle, but different software uses different trust anchor bundles. And each of these trust anchor bundles has their own requirements for inclusion, which means that not all certificate authorities are in all trust bundles. So let's talk about the Openssl bundle for a moment. That's what I'm highly confident 99% of you have on your Unix-like systems. However, every Unix tends to tweak it just a little. If you're using Red Hat, well, you get the certificates that Red Hat thinks you should have. And at least a couple years ago, Red Hat had their own trusted certificate in there for various purposes. So you should at least try to figure out what bundle do you have. And the other aspect of this is every Unix and Windows as well has set up its own way to manage these trust bundles. There are a bunch of different tools. Now, I think every sysadmin, when they realize that they have to trust a certificate authority that doesn't ship with their OS, perhaps it's even their company has their own certificate authority, and we need the internal CA certificate. You look and say, oh, all these certificates are in this directory. I'll just dump the certificate in there and it'll work. Yes, it'll work until you get an operating system update. Figure out how your OS manages the trust bundle, read the documentation, and follow the instructions. Otherwise, at some random point, that cert will get wiped out and you'll have a mysterious outage. And Openssl has a command line option, -ca file, that says, for this invocation, trust this certificate. And now we get to one of the perennial sysadmin arguments. What's in a trust bundle? If you could start looking at these bundles, you will see dozens of organizations that I have never heard of. Should I be trusting these people? Should I be trusting governments? Now, these organizations all need us to trust them. But do we need to trust them? And that is an argument that should be had over beer and pizza. I'm not going to belabor it any further. Just understand that this underlies the entire way TLS works. So if people have trust bundles, what about creating your own? Sure, you can. You can go in and take an existing trust bundle and look at all the certificates and audit the ones that you want to trust. Now, this is absolutely pointless for web browsing. So many people use so many different CAs that if you start yanking out trust certificates, you'll start piling up certificate errors. It is very educational, however, and you might want to try it on that basis. Now, this is useful for applications. Suppose, Craig Maloney's global enterprise has decided that they're going to buy all of their certificates from VeriSign for the mail server, for the IMAP server, for the internal LDAP servers, all VeriSign all the time. You could deploy on your application a trust bundle that included only the VeriSign trust anchors. And if someone managed to get a certificate for, Craig Maloney Global Industry from some other CA, it wouldn't work on your applications and they would throw up errors. And that is especially useful for internal-only apps like LDAP. So, are there any, we have a little extra time, so any questions on CA and what we've talked about so far?
Go ahead and raise your hand if you have a question. I don't see any questions so far.
No? Okay. So, how does this signing stuff work? It goes through what we call a chain of trust. Here we have the country of Gilder. They have a root CA. They have their trust anchor. And this is the diagram you would see in the early SSL explanations and still persists to this day. I want a certificate signed. I submit it to the certificate authority. They look at me, check my driver's license, say, yeah, you'll pass, sign my certificate. And the client comes along and performs certificate validation, which is finding a valid path between a trust anchor and the certificate provided by an application. So here, there's a very simple valid path. Now, that simple path is kind of a pain to use operationally. To sign a certificate, you must have the private key for the trust anchor, or rather for the signing certificate. A company like VeriSign or AT&T with those trust anchor certificates that they have spent hundreds of thousands of dollars and many years getting audited and verified. They don't want any schmuck to have the private key for their trust anchor. So what they do is they sign what's called an intermediate certificate. And us schmucks in the middle, we get to use the intermediate certificate to sign client certificates. Now, the trick with these is if you're running an application and you get a TLS certificate and it includes or it uses an intermediate certificate, you, the application administrator, must provide the intermediate certificate in your application. The client does not have this. This is a very common cause of misconfiguration. The client has no ability to go search on the internet and pluck out these intermediate certificates. That may be called a chain file, an intermediate CA file, anything like that. Now, the intermediate CA looked great until everything went horribly wrong. In the real world, you will see things like intermediate certificates getting promoted to root certificates or trust anchors. You may see, especially some of the older trust anchor certificates started to expire. It's been 20 years since the earliest SSL came out. So what we have today is something that looks a little more like this. You will have multiple CAs cross-signing each other's intermediate signing certificates, and all of those intermediates signing your certificate. And the client that wants to validate is looking for any valid path between a trust anchor and your certificate. Now, this looks great. This doesn't always work. A couple of years ago, we had a catastrophe on the internet where a trust anchor certificate expired and clients using OpenSSL could not validate the alternate path. So, if you're running an application on the internet, even if it's supposed to be stable and do not touch, you are committing to updating OpenSSL forever. Holes are fixed as soon as they are found, but this is the world we live in. Everything is complicated and tangled. So, still there?
Yes.
Okay, let's talk about OpenSSL. I'm sure many of you have looked at OpenSSL command lines and either screamed in rage or boggled in astonishment or just had your jaw flap open and say, what is this? Well, yes, OpenSSL is complicated. A big part of this is because cryptography is complicated. This is genuinely difficult stuff. Now, I'm sure if the OpenSSL developers could travel back in time to 1996, they would give their predecessors and younger selves a few hints on what they could do better. But this is a complicated problem space. And here we are. So, in general, using OpenSSL, you have the OpenSSL command, a subcommand, and then options. The subcommand sets the feature or cryptographic functions you're working with, and the options configure that function. So, one of the key parts of a sysadmin's toolkit is connecting to a port. I mentioned sending email by hand. Web developers may connect to their web server and see, is the server answering, or is my browser hiding everything? This is kind of difficult on a TLS protected service because you're speaking raw TLS by hand in a telnet session. I want to call it impossible, but if I do, some smart guy will point out a daredevil sysadmin who managed to pull it off under very special circumstances. So I'm just going to say highly difficult. OpenSSL has the -connect and -crlf options for connecting to a TLS protected port, much like Netcat or Telnet. Which one of those options you use depend on the new line handling and your Unix version, because the functionality changed between OpenSSL releases, and not all Unixes carried that change forward. Check your man page, or just try one, see what works. Now, this is a debugging tool. It will connect even to a self-signed certificate on a service. So add the verify return error to check the certificate and validate the chain of trust. So here, web browsers cache all kinds of stuff even when I don't want them to. I wanted to verify that my permanent redirect was still in place on my web server. I used this OpenSSL command line to connect to the server and manually entered the get/http:/11 and the host statement and 2 enters. And it flooded out a bunch of HTML, and then I got my 301 moved permanently. So yay, it really was in place, and I don't have to trust my browser. A couple things that can make using OpenSSL like this easy are the -quiet and -brief options that they hide all of the certificate stuff. One of the things that might affect you, it's easy to see if a server application supports TLS 1.3, but proving a negative is much more difficult. OpenSSL has flags to specify TLS versions, which one to use, and it also has a no version of those same options to forbid a version. Here I have an OpenSSL command line that forbids all modern acceptable TLS versions. And OpenSSL will look at this and do its very best to negotiate a working connection. If your application supports any bad versions of TLS, this command finds it. Okay, that's some basic stuff. Let's go on and talk about certificates. I'm sure most of you at some point have had to install a TLS certificate in a VPN client or a web server or something. A certificate really is an X.509 certificate. This is the International Telecommunication Union's digital certificate standard. It's built on ASN1, the same standard used by SNMP, used by Telecom, used by many other things. You do not need to know ASN1. Fortunately, you just have to realize that you're seeing ASN1 when you see a bunch of numerical garbage. Certificates also pillage the X.500 directory standard that's used in LDAP, which provides these identifier labels like OU, O, ST, and so on. Every label has an ASN1 identifier with an X500 identifier attached to that. So, this is a formalized statement of identity that expires usually every year, or nowadays every 90 days, perhaps sooner. A certificate has a bunch of components and stuff around it. The big thing that most of you have probably seen is the certificate signing request, the CSR. This is a file that you create that says, please, here is my information and my identity. Please sign me. It includes a public key, and it comes with a private key file. The private key is the secret for your certificate. Protect this at all cost. Anyone who captures that key file can use that certificate and pretend to be your application. The certificate file is an extract from the CSR that is digitally signed by the certificate authority. And you, as a server operator, you combine the certificate with the private key to authenticate the server. And again, protect that private key. If necessary, use a hardware security module, which is a physical device that the key cannot be removed from. Certificates are also validated at different levels. Domain validated means that the CA checked and verified that the entity requesting the certificate controls the host that this certificate is for. Organization validated means that the CA verified that the entity requesting the certificate belongs to the organization that controls the host the cert is for. And at extended validation, the CA verifies that the organization is a specific legal entity. The important thing to me as a sysadmin is that all of them provide the browser lock icon. Clients accept all of these. For a time, address bars turned green for an extended validation cert. This no longer happens. Sorry, I can't see my notes, so I have to touch one more point here. Which of these do you need? If you are bound by regulatory compliance, you may need organization validated or extended validation. If you are just running an application for, say, your car company or your ebook store, all you need is domain validated. If you are a financial institution, not that you take credit cards, but that you process and clearinghouse credit cards, or if you are offer the bank account insurance to your clients, you may need extended validation. So, the certificates can use two different algorithms. One of them is RSA. This is the old familiar where the key length dictates the strength. And today, 2048 bits is the standard. There is really no need to go any longer. Now, when I say that the key length dictates the strength, there are some people who say, well, I should use a 4096-bit certificate. It's twice as strong. And no, 2049 bits is twice as strong. A 4096-bit certificate is 2 to the power of 2048 times stronger and requires that much more computing power to validate. Using a longer key means you're making your clients work harder and slowing down your application. If you need that kind of strength, look at Ecdsa. This is a newer standard. Key length is not how it works. Instead, it uses something called named elliptic curves. It's roughly as strong as RSA, depending on the curve you pick, but it requires much less computing power. Which should you use? Well, if you're targeting mobile, Ecdsa is very mobile friendly. Now, let's talk about common names in a certificate. Common name is the most widely recognized part of a certificate. It's also the most incorrect part. A common name today could be an email address, a user ID, first and last name, or a device serial number. The common name was used to store host names until 2000, when it was deprecated. And yet, to this day, you will see brand new tutorials written say, here's how you put your host name's common name in a certificate request. It is wrong. It is being actively exterminated. On the other hand, some software expects to find a host name there. So, if you encounter software that's checking the CN for a host name, it's wrong. File a bug report. It has been deprecated for so long that the deprecation is allowed to drink in the state of Michigan. So, why is it deprecated? The CN can have a maximum of 63 characters, but domain names are longer than that. I have this domain. You keep using that word. I do not think it means what you think it means, .com. The you keep using that word part is, I think, 61 characters. Adding .com means the domain name itself overflows CN. CN is not checked against various TLS constraints. So using this in software is holding back improvements. The replacement is called Server Alternative Names, or SAN. If you want to look at a certificate, use the Openssl X509 command. This spills the contents, it spills the chain, identified entities in the certificate, any extensions in the certificate, and more. Okay, everybody's face has disappeared. Are you still here?
Yes, we're here.
Okay. So, host names in a modern certificate go by subject alternative names. And you can pull those from a certificate by checking the extension subject alt name. And it'll look like this: X509 version 3 subject alternative name. And here are all the host names in my certificate. Really, my true certificate has like 20 host names in it, but you get the idea. There's also this thing called the wildcard certificate. And it's good for any host in a domain or subdomain, like this wildcard.mwl.io. I mean, that sounds great, doesn't it? I mean, you folks who work for Ford Motor Company, wouldn't you like to have a X509 certificate that was good for anything in Ford and you could just slap it on any server you wanted? Well, the problem is you have to put the private key everywhere you want to use this certificate. If any one of them is compromised, the entire certificate is compromised. This means that every time you fire a technical employee, you would need to revoke and reissue that certificate, because otherwise they could, take that copy home on a USB key. And if an intruder is sneaky, you'll never realize that this certificate has been compromised. The safest use for a wildcard certificate is on subdomains that are dynamically allocated and where the hosts are dynamically created and destroyed. If you have some load sensitive DevOps stuff, that is where a wildcard makes sense.
Michael, we do have a question in the chat regarding the CN. What should go in the CN now?
Right now, I have two answers for this. One, whatever your certificate authority decides to put there. Many of them still put a host name in there. And some software expects to find it. So we're fighting to destroy that. It is legitimate as a common name to have, I had a list a couple slides ago, usernames, serial numbers, email addresses, VPN user identities and such. All of that works in a CN. So, revoking certificates. If your private key is compromised, if someone takes that key, you need to tell your certificate authority to revoke the certificate. Now, basically what happens is you contact the CA and say, hey, this certificate was hacked. Tell everybody not to trust it. And the CA provides notification over two different methods. Certificate revocation lists and online certificate status protocol. Both have problems. We'll get to those. If your CA offers revocation insurance, saying we will let you revoke your certificate and issue a new one without charging, or if you're using ACME with a free certificate authority, like we'll touch on, revoke on any doubt. I would even tell you before you have your application go live, revoke the certificate and test the revocation process. See how long it takes your CA to revoke. Behind the scenes, certificate authorities are all shell scripts. This should happen very quickly. So, in addition to these two protocols, Firefox and Safari distribute the list of unexpired but revoked certificates to their clients. Chrome provides a filtered list of only the important sites to Chrome users. I have a little tantrum here. I revoked the certificate for my e-commerce company. I sell books directly. It's like the minimum viable e-commerce system. So I revoked that certificate. I got a new one. And Chrome never provided that revocation notice to the users. This is a problem. We'll touch on what to do later. Chrome does, however, provide the revocation lists of very large companies like Amazon, and they provide revocation status of certificates of companies that give Google money. So, the older method. It's a file provided by the certificate authority, and it contains the serial number of all the certificates that aren't expired but should be rejected. Depending on your certificate authority, it could be as big as 75 megabytes, and it can usually be cached. The problem with the CRL is it doesn't scale well. There are people on the internet, even today, who have dial-up. Think third world countries, think some parts of the United States, and a 75 megabyte file is a big deal. So, and very few people really need the entire list of what's revoked. They want to know about a specific certificate. And that's why we have online certificate status protocol, where the browser says, oh, I have the certificate for Craig Maloney Global Industries. Let me check and see that it's valid. I'll poke the CA. And these notices are digitally signed. They operate over plain HTTP because they're digitally signed. And they're valid for 7 days. So the client can cache it. And if the certificate needs to be revoked within the next 7 days, the attacker has a shrinking window to exploit it. Now, the server can do this nifty thing where they make an OCSP query, attach it to the certificate when the client connects, and return it directly to the client. It's called stapling. And the client says, oh, I have a digitally signed OCSP statement. This certificate has not been revoked. And that makes your website faster. Now, the server can also set this header called must staple, where it says, if I don't staple a valid OCSP statement to this certificate, the cert is automatically invalid. Chrome and Safari, you have to enable that on the client side. Firefox just accepts it. Chrome in particular, you must enable OCSP checks on certain Chrome and Safari builds. Chrome, however, entirely ignores this must staple thing. So, if revocations are ignored, what do you do? Well, there's a couple ways to approach this problem. My favorite is to not use clients that ignore revocation statements. I do not want to revoke the certificate on my small company and then find out that Chrome users got ripped off. We can have short-lived certificates. We'll talk about how to do that. But if you're handling a lot of money, certificates that are valid for only 24 hours may be a real good solution. There's something called DANE, where you can publish certificate fingerprints in DNS, but this requires DNSSEC and is only really used in the email space. You could also choose to deploy forks of browsers that only enable OCSP and must staple and such. You can also store the private key in hardware security modules. And HSMs range from everything from a little USB device you plug in to a 1U rack mount unit that is fitted with explosives that detonate if anyone opens the case. This may not be tamper-proof, but it is decidedly tamper-evident. So, to get a certificate, you have to create a CSR. And the CSR needs to contain the information that you want the CA to validate. You've all seen the friendly Openssl dialog, and it's obsolete. We're really trying to kill it. And yet it persists in tutorials because nothing on the internet ever dies. So what do you do today? You use a config file or generate entirely on the command line. Once you have a CSR, you could technically reuse it to renew your certificate, but this is terrible practice. The CSR is tied to a particular private key. Many sites get broken into and never realize it. Are you certain that your private key did not leak? Have the CSR standards changed since last year? CSRs are free. They can be created by scripts. Make a new one every time you renew the certificate. Now, what information should go in your CSR? If you're getting a DV certificate, you only need the host name. You don't need to put your company name or the state in or any of that garbage. If you're getting a more highly validated certificate, you need that organization information. Get a list of that before you start creating the certificate. Maybe everybody that works for your firm calls the company the pit of despair. However, if the organization paperwork says that the official name is the Pit of Despair LLC, the certificate authority will reject the request. Look it up before starting. And you'll see a few X500 codes. A C is the two-letter country code. ST is the spelled out state or province. L is the locality, the actual locality where the paperwork says your organization is, and O is the company name. This lets you create a config file like this. Here I've specified a bunch of things like prompt set to no, don't ask me for details. I've set the bits and the file names. You'll note I did set a CN in this because some software is going to poke for it. However, at the bottom, I've set up this little array of alternative names, of subject alt names that I want in this certificate. And I use the certificate to, I use that config file, and I use the Openssl rec command, tell it to generate a new key, use -config to point it at my config file. Note that I named the config file after the domain, the primary domain that the certificate is for. It generates a key, asks me for my passphrase. There we go. Now, I don't know about you, but I always wonder when I have a CSR and it's this file of binary garbage, is this really the right file? You can use Openssl rec to read a CSR and make sure everything is the way you wanted it before you send it to the CA. And here I'm generating a CSR entirely on the command line. I don't know about you, but if I have to generate a new CSR every year, that's exactly how long it will take me to forget everything. But putting this in a shell script is trivial, and you can comment it. You can even run a cron job to say, hey, generate a new CSR for me in 365 days from today, or 360 days, whatever it is, and renew your cert. Here's a little tidbit about CSRs, because we tend to hang on to certificate requests long after they're invalid, and sometimes we scramble up the files and forget which one we need. The modulus is a shared numerical value unique to a public-private key pair. And you can examine them, you can extract the modulus from CSRs and certificates and keys. The reason I bring this up is a nifty trick. You can have your network management system check the modulus of certificates installed on your servers. Don't go overboard with, every 5-minute Nagios checks, but once a day, check this. And if the modulus has not changed for more than a year, someone reused a private key in renewing a certificate. And this lets you catch that kind of laziness. So, do we have any questions before I go on? Just pop them in the chat. Okay. Is anyone here?
Yeah, we're still here.
Okay.
Question, should the modulus be the same for all 3 files?
Yes. Yes. The modulus is a number for a particular private key, public key pair. And it should be the same between the certificate, the private key, and the certificate request. And it's a long, nasty number. Oh, yes, I was showing these files do not go together. These do not match. And it is such a long, nasty number that it is easier to compare it by piping it into MD5. MD5 is not MD5 is not cryptographically secure. But for most of us, for our own files, it is eyeball secure. Gumnos has a question that I will touch on at the end of the talk, because that is more of a rant than an answer. Oops, wrong button. Okay, I hit a button on the browser. Tell me you're still here.
We're still here.
Okay. So let's talk about ACME. Renewing certificates once a year kind of sucks. It's exactly long enough for you to totally forget everything involved and to even forget that you need to renew the certificate. Also, TLS is valuable on the web. There is a push to put encryption on all websites. Whether or not this is a good idea or necessary, or how necessary it is, etc., this is a pizza and beer discussion, so I'm going to put that off. But the Internet Security Research Group has made it possible by creating the Automated Certificate Management Environment. That's a typo on the slide. And it created a free CA. And this free CA provides 90-day domain-validated X509 certificates to everyone. So, and 90 days is just long enough, is just quick enough that you really want to automate this. It's no longer a one-off once a year thing. It's no, this is a routine task. I got to just make this happen. So, domain validation. This is where the CA verifies that the entity requesting the certificate controls the host. And it's highly amenable to automation. The client starts this little dialogue with the CA, and basically the CA challenges the client to change the host in some way. And if the client satisfies the challenge, the CA will sign the certificate. There are 3 kinds of challenge today. HTTP 01 is basically put this file in a well-known location on the server. The DNS challenge says make the change in the DNS. And ALPN 01 says make this change in this TLS protocol ID on the target host. There was a challenge called SNI 01, which was also TLS based. However, it turned out to be a really bad idea, and it has died a well-deserved death. Which should you use? Well, for someone like me with a single server or with individual servers managing certificates locally, HTTP 01. For a wildcard certificate, or if you need a certificate for something that does not speak HTTP, the DNS challenge is your friend. If you're running a server farm, if phrases like load balancers and clustering and, oh God, not again, are applicable to you, ALPN 01 is how you want to do it. So these 90-day certificates, they're automatically handled, but you want to start renewing them about 2/3 of the way through their lifetime. This gives you 4 weeks to resolve transient issues. If you try once a week, this means once it fails, twice it fails, and you say, oh, I guess this wasn't transient, I better look. And you still have a couple weeks to figure out what's going on. And most ACME clients just handle this. And let's talk about some clients you can get. CertBot is the official Let's Encrypt client. It's written in Python. It's distributed by default and more than one Unix OS. Some other ones I like, though. Apache has an integrated Let's Encrypt module that handles ACME for you inside the web browser. It's not complete. People are working on it. My favorite, of course, is OpenBSD's ACME client, if I happen to be on OpenBSD, because it's incredibly simple. There's a Docker container if you're not into simple and like complex, and it handles the entirety of ACME for you at the expense of using Docker. My favorite cross-platform client is Dehydrated. It's light enough that it can run on a Raspberry Pi without strain at all. Okay, I'm about to begin a new section. So, Proxmox has ACME in it now. Cool. I'm expecting more ACME everywhere. So, any questions on ACME before I head on to some tidbits? Okay, here is a bunch of stuff that I would normally cover in a real rush at the end of the talk. But I've had slightly more than an hour, so I'll go slightly slower anyway. Once you get all of your servers up to TLS 1.2 and 1.3, check out these things. HTTP strict transport security is a header that your web server can send to a client that says, this website only serves pages over TLS. Please cache this information. The client rewrites all HTTP requests into HTTPS, and the client refuses to check HTTP from this host name. This is a way to upgrade to TLS and enforce it. All the big web clients support this. It's something I might use on, say, mug.org, because I see you guys answer both HTTP and HTTPS. Next tidbit, certificate authority authorization. It's a DNS record that lists which CAs may issue X509 certificates for this domain. It is not yet mandatory, but one day it will be. Here, my first entry shows an example of DNS records that say, Let's Encrypt may issue certificates for my hosts, but I'm using the issue wild statement to say nobody can issue a wildcard. Wildcards are forbidden. And here is a second example where I have two different CAs. One can issue regular per host certificates, and another CA can issue wildcard certificates. Now, once you've got TLS working, I mentioned earlier that the NSA said bad things about certain TLS 1.2 configurations. How do you know if you're supporting this? Well, you test your server. The easiest way on a public web server is the SSL Labs testing engine. It looks for bad TLS versions, broken ciphers, general misconfiguration, cats and dogs living together, and other sorts of total chaos. The catch with SSL Labs is they send a whole bunch of queries really quick to your website. If you have intrusion detection, this is exactly the sort of probing that a wannabe intruder might aim at your server. Check with your security department before setting off the IDS. Or if you want to test it privately, testssl.sh. It isn't as pretty, but it's in shell, runs at the command line, and it can be used on internal sites. Okay, next tidbit, certificate transparency. You've probably all seen in the news at some point how some CA got fooled into issuing a code signing certificate for Microsoft or a certificate for Google's website. CAs can be fooled. They have been fooled. They will be fooled again. Pardon me. Certificate transparency is a way for you to check what certificates have been issued for your domains. Many sites offer this information. Google Transparency Project, crt.sh, there are others out there. People build them. You can check your domain names and see who issued certs. Are there any surprises? If you are in charge of security for a company and your policy is that only Verizon or VeriSign may issue certificates for you, you can check certificate transparency and you see that, oh, over there, Gumnos's project, his server is using a Let's Encrypt certificate. I better send the goons to go have a conversation with him. Again. So, certificates contain signatures that they were submitted to a transparency server. And one day, browsers will reject certificates that don't have those signatures. Next tidbit, sample failure. It's great to say that your client works, but how does your client respond when things go bad? The bad SSL website has expired certificates. edge cases, stuff that's technically legal, but doesn't often work. I talked about server alternative names. Does your application work if it hits a site with 100 names? How about 1,000 names or 10,000 names? Bad SSL lets you check all this insanity. Finally, running your own CA. Many companies do. Many companies will run a private CA for their private stuff. They have a private root certificate that all the hosts have to install. The Openssl suite includes a small CA. But this is intended as a learning experience, not for long-term use, not for multiple users, and not for exposure to the internet. This is something that the Openssl CA is something you run at home as a learning experience, kind of like you build your own firewall. You do it once or twice as an education. You learn what you need to learn, and then you stop doing it. If you're using this for a real company, you might use EasyRSA, DogTag, one of those. A big organization might use Free IPA or EGBCA, or they might buy a commercial CA product. And one of the reasons that you might run your own is so you can have a name constraint CA. This is something I'm really looking forward to. A big company can buy a signing cert that allows them to sign certificates in their domain. Basically, they have an intermediate CA. I could buy a cert that lets me sign anything in my domain and make each cert good for, say, 10 days or 24 hours or 12 hours. This sort of thing requires extensive, reliable automation. And so you need Puppet or Ansible or something before you even think about this. Name constraint certificates are currently expensive. However, they can be issued by any CA. This means I fully expect a race to the bottom, and they will eventually become less expensive. Even today, if your certificate, if a name constraint CA costs, $10,000 a year, but you have a big web farm and you buy a lot of certificates from an extended validation organization, you might check out the price of a name constraint certificate because it may be cheaper and it may even increase the safety of your certificates by being able to roll out these 10-day certificates. And companies are effectively and practically doing this today. So that is really it. And at this point, I will take questions. The book is a thing. You can grab it if you like. If not, who cares? And I've shut down sharing. And I hope you're still there. Okay. I got Jitsi back. Hello, are people? Okay.
Absolutely a thing, by the way, and you should pick it up. You can head on over to Tilted Windmill Press and pick up a copy of it. I'll post a link to that in chat. So there.
Thank you for the shilling. I appreciate it. So, okay. Another question from Gumnos. HSTS does not prevent you does not prevent you from renewing an ACME cert. Let's Encrypt will ignore it. So, yes, you can bootstrap yourself back into ACME. And those of you who have to bail out, thank you for showing.
Are there any other questions? Jason, go ahead.
Let's see. I'll defer to Jim because he had his hand up before I did. So,
sorry.
Come to me next.
I posted a link in the chat window for Mozilla's SSL config website.
Yep.
Incredibly helpful.
Yep.
For figuring out how to best configure your server to enable all the right ciphers and turn on or off all the proper options. I use that I use HA proxy as my termination point for SSL.
Mm-hmm.
And I use that SSL configurator to figure out what to put in my HA proxy file.
Yes.
Incredibly helpful. And then once I do that, then I use that SSL test SSL site that you mentioned, the Qualys SSL Labs thing. And it always makes me smile because I'm able to get an A+ rating on my sites by following those guidelines. Incredibly helpful.
SSL Labs does have the advantage that it's one of the few places a sysadmin gets positive feedback for stuff nobody can see.
Yeah. Well, if you do it right, I didn't always get an A+. I'll tell you that. but going through that configurator site just solves all the. It gives me all the answers to all the millions of questions that you have to go through to get it right.
Yep.
I have a second thing about the Let's Encrypt thing. I don't use it. I have this feeling, maybe you can tell me I'm completely wrong, that there's two things you want to do with TLS. One of them is encryption, as you pointed out, and the other one is identification.
Mm-hmm.
I always feel like Let's Encrypt is great for encryption. I don't trust it for identification. If somebody gets a hold of your DNS, it's game over, right?
Oh yes.
Yeah. Where if I actually do a real validated cert for my domain, I have to jump through a lot of hoops to get it right. Authenticating who I am.
Yes. So are you buying organization validated certificates?
Yes.
Okay.
Well, for my
That's a different
public facing, yes. For my public facing internet sites, yes.
Then you're doing something different. If you are buying the $20 buy SSL certificate,
Yeah, no.
that's domain validated. And realistically, if someone broke into your DNS and you were getting an organization validated certificate, if I broke into your DNS and I stood up my own competing web server on your host, on your host name, the first thing I would do is fire up Let's Encrypt and get a TLS certificate.
And that worries me.
Yeah, anyone can do it now.
Yeah,
Yeah.
It's like they've lowered the bar for masquerading as me.
The bar was already lowered.
Yeah.
All that Let's Encrypt did was make explicit what the domain validated cert is. It's actually better validation than you will get from by SSL.
So what are we to do? Just resign to the fact that
Here we are.
Pointless.
Here we are. The moment they created domain validated certificates, this was inevitable.
Yeah.
What I would prefer to see is that ACME or a successor protocol become mandatory for all domain validated certs, because at least there is some validation.
Yeah. It doesn't leave an easy feeling for me.
No, and it shouldn't.
And I understand your point.
Yeah, it's just here we are.
Yeah, and for my internal sites, I can't use Let's Encrypt because they have to be able to get to your internal site to do it.
No.
So for that, I run my own CA, and
Right. So
of course, I have
that
to
same
install
problem.
I have to install my CA cert in all of my browsers, which sucks.
Yeah, or you could use Let's Encrypt with DNS validation. And that will let you get publicly valid certificates.
Yeah,
and then you have the trouble of distributing them to the servers, and choose your headache.
Yeah. Yeah, right.
Would you like your left kneecap broken or your right?
Yeah. Hey, your choice. Well, okay. So I appreciate your thoughts on that, and this is a fantastic presentation. I'm really enjoying it.
Thank you. In short, it sucks to be us.
Jason, please go ahead.
Okay. Hey, Michael. I did Baby's second TLS. I tried to do Baby's second TLS project about a year or two ago. This is going to make chills go up and down your spine.
Oh, no.
Caching web proxy.
Uh-huh.
So basically, back in the day when everything was unencrypted, Squid worked great. Not so much anymore.
Uh-huh.
The situation is it's on a residential line, so there's no domains, and it's on a narrowband connection, so there's not a lot of speed going across it, which is why, you want something caching there. So the issue is it even worthwhile to pursue that anymore? Or yeah, it's like, okay, well, this is internal to a NAT, so Let's Encrypt isn't going to work. Like we just touched on the CA, we could run an internal CA, but that requires distributing certificates and blah. And then you have to deal with, okay, well, I can do my man-in-the-middle stuff, but then if I encounter a invalid certificate, what do I feed my client? So I'm sure that somebody has looked at this problem in the past and has come up with a clever solution, but I am at a loss.
I think you're really in another choose your pain situation. I would encourage you to do some reading and see what other people have done. In that situation, personally, I think I would give up on the caching proxy.
That's my current solution.
Yep.
So, yeah, I just wanted to hear that from somebody that has more extensive knowledge behind this whole TLS rigmarole.
I have no magic for you.
So on a slightly related case, but not entirely related, what would you suggest for man-in-the-middling for old systems that don't receive TLS updates anymore, such as For example, an old IRIX machine or an old Windows 3.1 machine. Something if you're a classic computing enthusiast and you want to go on the internet.
Oh, well, that
Other
is
than
where I would
don't?
look at. I would look at an explicitly configured squid proxy, which
Okay.
I just said I would give up on. But
this is the world we live in nowadays. Yes.
yes, there are OpenSSL packages for various Unixes that include bad SSL, like SSL3 and SSL2. So I would grab one of those, link it into Squid, and man in the middle it deliberately.
Delicious poison.
Oh, yes. Yes.
Okay. That's my questions of the day. Thank you.
My pleasure. Next.
We have some questions in the chat. NJ Doyle asks, any quick thoughts on client certs that are effectiveness, a good solution for edge cases?
Oh, client certs. I have mixed feelings on this. In short, client machines are a trash fire. Really containing that client cert and protecting it on your average Windows machine where the user can use it, but an intruder can't grab it, is difficult. I mean, look at the ransomware attacks. Some applications use them. I would say if you use them, set up your own CA, require use of a passphrase, issue new certificates frequently, and hope.
Always hope, huh?
Always hope.
Excellent. One more question here from Jacob. I'm looking to implement certificates in a private network environment for Wi-Fi and port security. Is a self-signed more than sufficient if you are distributing the certs yourself?
Oh, yeah. There's nothing magic about a trust anchor, except that the person who owns the trust, a widely distributed trust anchor, spent millions of dollars on the exact same digital file that you can create in 5 seconds at the Openssl command line. Self-signed is perfectly fine. You know, if you can't afford store-bought, homemade is just fine.
I won't regale you the tale of one of my previous companies where we had our own mail client stuff in that, and we had to pass around certificate bundles to everyone. That was fun. Yeah. Zimbra, if I'm remembering. Yeah.
Well, earlier Gumnos asked about file extensions.
Yes.
The whole NIVX for the 8021X stuff, this is another argument best had over beer and pizza, because different organizations have wildly different stances on it. I encourage you to enjoy that argument at your convenience.
So the next time we can have beer and pizza in person.
Yeah. You can argue this all kinds of ways. So the file extensions. File extensions are meaningless in Unix land. However, the They are useful for the human operator. Generally speaking, these extensions like .pem and .crt or PK7 represent the encoding on the file. However, a whole bunch of sysadmins don't understand the encodings. So I've been in more than one system I've been called in to troubleshoot where all certificate-related files had file names ending in .crt. And I believe that Craig right now with his facepalm speaks for all of us. So, yeah, the extensions just mean the encoding, or they mean the sysadmin is an idiot. Or they mean some previous sysadmin was an idiot, but changing the file name extensions would be a lot of work and might cause outages and perhaps would even have to go through change control. So we're not going to.
Gib asked the question, how can I distribute a cert to people I don't know? I guess if I can provide a website to provide it, any easier way?
That's really as good as it gets. If you are, presumably you're distributing, well, if it's a search for an application, the application should distribute it automatically, like your web server or your mail server. If you're talking about a private trust anchor, which is what most people are trying to do when they ask this question, yeah, a website, you could email it and sign it with PGP. There's no great solution for this.
And one last question here. I believe for some services, like previously Freenode, Ask Austin, allows SSL certs for authentication. Would a self-signed cert work for that use case? And should the key length be greater than, and should a key length greater than 248 be used?
I'm not aware of any reason to use a key length greater than 2048. A 2048-bit key is uncrackable within the lifetime of anyone on this call, barring new methods of attacking the algorithm.
For vampires.
No, including vampires. A longer key is not crackable within the life of the universe. So I don't see any reason. Now, would a self-signed cert work for if you're running a service and you wanted to provide certificates to authenticate your users? Yes, absolutely a self-sign is enough. OpenVPN does exactly that and is distributed through many places. And yes, the OpenSSH people are starting to use 3072-bit. They have a much narrower and more specific use case. And I think that there is a little bit there's a little bit of attitude in that decision. They're kind of saying, bite me.
Yeah, some Cisco routers, according to Jacob, some Cisco routers, I think the upper limit is 4096. Newer iOS, this is probably different.
Yeah, there are cryptographic things with the 4096-bit limit that I do not understand. I trust the cryptographers when they tell me that there are issues with crossing that boundary and going up to like 8192 or something.
Okay, thank you so much. Any other questions? Feel free to put them in the chat. But I think we're going to wrap things up.
Yeah.
For the time being, I have a list of folks that would like to win a book.